point A to B minus EC, say, DL, okay? Going around from A to B, now we actually go in the opposite direction to I1, okay? But then we have to integrate, to get the potential difference, we have to integrate EC around that loop. Now, EC is not the thing that's been driving the current. Remember, it's the EI, induced field, okay? But it's something that pops up because the equation has to be true, okay? So we can find EC is going to be J on sigma, okay, minus EI, okay, any induced fields, okay, at a point. And they're going to be, obviously we're going to have two components to that, okay? Say we're looking at loop 1, so it's going to be EI11 plus EI21, okay? So the self-induced field from the current I1 and the induced field from the current I2. Okay, so we have to do that, the integral AB equals minus integral from A to B, J, and here we're talking, say that loop 1 has some conductivity sigma 1 and it has some actual area, A1, we'll get onto that later, so it has some conductivity, minus EI1 plus EI21, okay, DL. We're going around, note that we're going around the opposite direction to where we did these other integrals, okay, so we're going to get some negative signs coming in. So we can separate that into different bits, okay, so we should note that J on sigma 1 dot DL, okay, and the DL that we're defining now is actually going opposite to the one that we did the calculations before, okay, equals minus I1 of T on sigma 1 A1, so that the actual cross-sectional area of the wire is that's going around the circuit is A1, okay, times DL, which is not a vector anymore, okay. So we could also define further if we'll bring this down. Okay, so that's going to be A to B I1 of T sigma 1 A1 DL, okay, and then we're going to have integral from A to B, okay, minus, okay, EI11 plus EI21, okay, DL, because whereas this is not a vector anymore, okay, because the direction of DL in this case, because we're going from A to B, is different from when we did the calculations for the electromotive force, okay? So we can work that out, and we note that we define the resistance of the circuit to be basically integral A to B of DL on sigma 1 A1, okay? So if the circuit's made of a bit of wire with cross-sectional area A1 has conductivity sigma 1, and the length around the circuit is going to be integral of L, which will be big L, okay? That would be equivalent to a resistance, okay? What we're trying to get, resistance, okay? So we end up with sigma AB equals R1 I1 T, okay? And for these terms, okay, these are just, because we've said that, this is infinitesimally small, okay, it's effectively the same as the EMF right around the loop, okay, because we said that these things are very close together, okay? So basically, these integrals from A to B, because A and B are almost touching, okay, are the same as these integrals we've already done, okay? Okay, so this is going to be, so this one is going to result in the E11, okay, and this one will result in E12, okay? So they're going to be plus L1 di1 dt plus M, the mutual inductance di2t, okay? So you might want to call this VAB, the voltage difference between the two, because that's what you measure with a voltmeter, okay? You measure the difference, okay? So there we've used EMT to sort of relate a magnetically coupled circuit to something that looks like we'd have in circuit theory, okay? Remember, these are the sort of put together an inductor or transformer, these parameters M and L and R, okay? So we'll go through this again in the probably one of the track classes, because it's a good example. So we could do that for loop 2 as well if you wanted to. And you see that you could then have effectively a two-port model, okay? So, this would be, V1 would be the port AB, okay? And V2 would be the port CD, okay? And then you have, from those calculations and from knowing what M and L are, by doing the integration numerically, or if it was a very simple structure, you do it analytically, you'd have a circuit model for that transformer. Go on.
You were talking about, when you were working through, you were talking about the direction of delta L or DL.
Yeah, that's important to me. Okay, so in this case, when we do these EMFs, okay, they're assuming that DL, because from our definitions before, okay, from way back, okay, for what A is, okay, we defined the DLs to be in, so if the EMF is equal minus the partial derivative of time is A, right? And that A is defined with the DL as a positive going in the same direction as the current, okay? If you check it, it would be that way. I mean, if DL was in the opposite direction, then you'd have to put a minus sign there, right? Okay. So DL is that could be, yeah. I think that this actually is, in this case, I'm not so sure about that, but But getting back to your question, the A to B, but then we want to find the potential between A and B, okay? And so the potential difference is the integral of from A around to B, okay, of EC, okay? And it's an integral done with a DL, okay? But in this case, the DL is going in the opposite direction to that one, okay? So we get a negative sign for these ones, okay? Otherwise, so these EMFs, okay, which are also integrals of the electromotive force around the loop, but the way we did that integral is opposite to the way we're doing the integral for potential, okay? So that's why it all comes out like this. Does that help? Okay, so that was just a good example to link, EMT theory to, circuit theory.